Good morning, everyone. My name is Ruxandra. This is Moritz, and together during the past semester, we've been working on our bachelor thesis entitled Over-the-Air Federated Learning Under Limited Communication Resources. This represents a study of compression-induced error feedback in bandwidth-limited settings.
So in this thesis, we mainly explored the area of machine learning. So in machine learning, it's been shown that models require a lot of data for training. And it's generally been shown that more data has resulted in better models. And this has kind of been exacerbated by the rise of IoT, which has led to data being stored in many different locations, as well as being generated in many different locations. And with this, it's also brought up the concern of privacy related to sharing overall data as well. In machine learning, there are two main learning paradigms. There's the centralized method, in which all data is collected from devices to a server without any local processing. And then there is the decentralized method, which is including federated and distributed learning. In this thesis, we are focusing only on the decentralized learning paradigm, more specifically the federated learning.
Right, so now that we have theoretically introduced the topic, let's take a look at how it actually works, namely at a federated learning architecture, which is illustrated in the picture on the left. In federated learning architecture, there are two main roles. First, we have the coordinator, which is on the upper part of the slide, and in the lower part, the agents. When we say agents, we refer to any smartphone, any laptop, any device, any IoT device, basically that has a computational power to produce data and ultimately also work on it in order for training. At the same time, each agent performs multiple local epochs, as indicated by the arrows in the lower part. By epoch, we mean that each agent goes through the local data set, at least one time. After they have gone through the training locally, they send the model updates in the aggregation stage back to the coordinator. Once the coordinator has received all model updates from all agents, it averages them and then performs the broadcasting stage to update the new global model. So just a quick recap, we have exact roles, one coordinator and many agents, and at the same time, we address the privacy issues highlighted in the slide below, as we do not share raw data and only the model updates.
If we now take a look at federated learning from a more mathematical perspective, we can see that the goal of federated learning is to solve the following equation, where we're looking to find the set of parameters W, which minimizes the objective function f. Here, f denotes the summation of the local loss functions fk subjected to a local weight. So this is the coefficient pk. And pk can be said to be essentially the importance which we place on each device. But in general, this has also been observed frequently to be just 1 over m, denoting the arithmetic mean.
So if we go back and take a look again at the architecture to recap, we identify that each agent basically represents a subset of the entire data set that is in the end used for training. They only share local model updates to the server, and they perform at least one epoch in between transmissions. However, when we talk about a federated learning architecture, we're talking about a very large number of devices that have to take part in training, and they also share very long messages to the coordinator. So this is exactly when communication bottlenecks occur. And these communication bottlenecks are even more problematic, given that in most applications, these agents communicate wirelessly, and wireless domains are defined by limited bandwidth. So a few examples of applications where federated learning is used in real life. It has especially a positive impact on organizations and institutions that have to process data under legal and ethical constraints. And to give some examples, we are talking about hospitals where we need patient data for training, industrial engineering, or even text predictions using personal messages.
So if we now look at how some of these communication bottlenecks can be addressed, they can be addressed in three main ways, as highlighted by the literature. The first way that we can approach this is by using partial participation. This is where only a sample of the agents are included for each given aggregation stage. Furthermore, we can use local training, in which more than one local epoch is performed in between the transmissions, which is used to basically share more relevant data. And finally, we can also use compression, which is the main focus of this thesis. And in compression, we can use either a lossy or a lossless compression. But the more interesting route to go down in our case is the lossy transmission, because in this case, the model accuracy may be affected because some information is eventually lost at the receiver. So compression can also be either unidirectional or bidirectional. For the unidirectional case, we can either transmit only on the uplink or the downlink, but in the bidirectional case, we do both.
Yes. So in this thesis, we have basically focused on the compression as Moritz highlighted. However, we have combined it with a technique called error feedback. And in this thesis, we have tested two compressors, namely RAND case sparsification and quantization. But let's take a look at what these terms actually mean. So if we take a look at this figure on the left, when we mention compression under the form of sparsification, we mean that from a given set of parameters that have to be sent to the coordinator, we only select a few that we sent in the original form. So we don't compress the very few that we have selected. On the other hand, when we talk about quantization, we send all parameters, but each are individually compressed. So think of it as a file that you zip it and then you send the zip file. That is basically quantization. We compress individually and then send everything up to the coordinator. However, as you can see, we are not sending the entire data back to the coordinator. So we are missing some data and therefore the model accuracy may be affected. That is precisely why we combine it with error feedback in order to keep track of of the data that has not been sent. So how do we do this? Let's take a look at a very simple example to understand the technique of error feedback. Imagine that you would have to send a 1.3 back to the coordinator. So you send a 1 because you need less bits to send an integer value rather than a floating point. However, you save locally the value of 0.3. Then in the next transmission round, let's suppose you have to transmit a 2.7. First, you add the previous value that has not been sent, which is highlighted in yellow, a 0.3, which results in a 3 that in the end gets transmitted. So this is how we keep track of what has not been sent, and then in the end, send it. There are, of course, different levels of compression, and the higher the compression level is, the fewer bits are needed for that specific transmission.
And if we now take a look at some of the key points which stuck out in our literature review, we see that federated learning was first introduced by Google in 2016, which means that it's quite a recent field of research. There are many different available algorithms, FL algorithms, and these include, among others, Fedlin, Tamuna, etc. Federated learning algorithms do not share raw data, only model updates. And this fact has led to improved privacy since we are not sharing the raw models or the raw data, but this has still been proven to lead to some data leakage. So there's still a need for enhanced privacy in federated learning algorithms. So as a conclusion, we identified a research gap in secure FL algorithms that are also communication efficient in wireless domains. This led us to a problem statement. So the significant social and engineering importance of FL, as well as the communication bottlenecks, led us to the following problem statement. So we set out the following research question: how can communication bottlenecks during federated learning be reduced by compression while enhancing accuracy through error feedback? And this led to two goals, the first being to gain theoretical and empirical understanding of the benefits of combining compression and error feedback for a state-of-the-art algorithm. And secondly, to determine a suitable algorithm which incorporates compression while also preserving the accuracy of the produced global model through error feedback.
Yes, and now a bit more in detail about our work specific in this paper. So our work built on a federated learning algorithm named FedPLT, which was designed here at KTH in the Division of Decision and Control Systems. Our contribution represents in adding the compression mechanism together with the error feedback mechanism on top of the federated learning algorithm, called FedPLT. And what is unique, at least to the best of our knowledge about FedPLT, is that it is the only algorithm to provide rigorous privacy guarantees through differential privacy. And last but not least, throughout the paper, our work represents an applied research, which can be summarized to algorithm design and analysis, where we tested 2 compressors, quantization, and run case falsification. And now if we take a closer look at the results, we have run 3 separate experiments on FedPLT upon upgrading it with the compression mechanism. The first one represented unidirectional compression from the agents to the server using run case falsification. Then we ran the exact same experiment, however, this time with quantization. And finally, it was bidirectional compression using quantization. 2 types of tests were run. First, optimality tests. These tests indicate how well the algorithm minimizes the loss function that was presented a few slides ago. And at the same time, we also ran accuracy tests. These indicate how accurate the algorithm output is based on a given unseen input. And finally, the results have been evaluated based on 3 separate metrics. First, the model accuracy, the model asymptotic error, and also the model's convergence rate.
So we now outlined the procedure that was carried out for each of these 3 separate experiments. So the first step was to generate a training problem. We would then simulate it with and without error feedback. And this meant recording the values of the metrics, which include the accuracy, convergence rate, and the asymptotic error, against 3 separate independent variables. And these independent variables were the number of agents, the number of data points per agent, and the number of features per data point. And the reason we did this was to kind of expand our view of the problem and allow us to give a broader conclusion to the experiments. So after that was done, we took the element-wise the element-wise difference or the ratio of the 3 parameters. We then graphed the differences or ratios individually. And from this, we were able to extract the observations and conclusions, which we present to you in the next slides.
Yes. So one example of such slide that we generated upon the very first experiment, which was RANK unidirectional compression, where we only vary the agents, was the difference in convergence rate against the number of agents. When we say difference in convergence rate, we mean that we graphed the difference of the convergence rate when error feedback was activated minus when it was deactivated in order to see whether the convergence rate is improved or worsened once we activate EF. So if we take a closer look at the graph, we can see that when we hit 50 agents or more, using EF constantly worsens the rate of the convergence as its value increases. So we can conclude that in this experiment and in this specific case, the greater the number of agents are, the greater the cost of the convergence rate basically becomes.
And now we take you through the same experiment, but this time we're measuring a different metric. So this time it's about the ratio of the asymptotic error. And here from this graph, we can highlight 2 main points that stick out. So when using more than 20 agents, error feedback consistently improves the asymptotic error. And we can tell this by considering the ratio, which is calculated as the asymptotic error when error feedback is turned off, divided by when error feedback is turned on. And because this ratio is clearly above 1 for all values above 20 agents, we can tell that the asymptotic error when EF is off is much greater than when it's on. And we can actually see that the order of magnitude of the ratio is of the order of 3, which means that there's an improvement of roughly a factor of 1,000 here. And if we continue, as the number of agents increase, the benefits of using EF seemingly increase as well. And this is shown by the increase in the magnitude as the number of agents increase as well. And one last point is also that we see that there's somewhat of an exponential relationship here.
So of course, for all experiments, we have run this type of simulations, then we would graph it. We don't have the time today to run through all of them. We just wanted to give you a few examples. However, we have collected the main results gathered from all 3 experiments. So the main results are as follows. First, in terms of asymptotic error, when we use error feedback, we almost always observed a lower asymptotic error. However, the accuracy does not follow the same trend. We actually have indeterminate results in terms of accuracy. Across all results, however, the convergence rate is worsened by using error feedback. So it is fair to say that this seems to be the main cost attributed to error feedback. At the same time, the effect of error feedback can be both mitigated or amplified by varying the number of agents, features per data point, and data points per agent. And last but not least, these effects are unique to each compressor we tested, quantization and RAND case falsification.
And now to kind of conclude our work, we highlight that this thesis was both of our first experience with conducting research in an academic setting. And we both believe that we have achieved the goals that we initially set in the beginning of the thesis. And we would also like to say that time was the main limitation in this paper, as we were only allocated 20 weeks worth of work. And furthermore, we see that federated learning has enormous potential to improve societies due to the added privacy, which opens up more data in the use of training. And we also highlight that future work regarding this thesis can be split into two main parts, which we will discuss now.
Yes, so more on future work. If we were to continue this thesis, let's say next week or tomorrow, there are a few steps that we would take. So on a narrower view, the next obvious step would be to test other types of compressors. We remind the audience that in this thesis, we have only tested quantization and RAND case falsification. So it would be very interesting to see how FedPLT would behave if we changed the compressor. At the same time, we acknowledge that a single level of quantization, which is 1,000, has been used throughout the experiment. So it would be very interesting to vary the level of quantization and to understand the relationship between the quantization level and the number of magnitude that we gain by activating error feedback. In a broader sense now, most applications, there are more applications of federated learning that can be explored. And one application that comes to mind is the space industry, where we identify a need for novel algorithmic solutions that allowed training machine learning models on board. And that basically concludes our presentation. Thank you very much for listening.
Thank you.